In this video, I'm going to show you our ultra low cost 2.7 GHz active probe.
To kick us off, we're going to look at a signal with a very fast rise time and how the probe loads and affects the signal when it's attached. Because of the probe's 0.7 picofarad tip capacitance and the resistive tip, this loading should be very minimal.
Right, so here we have our setup. We have a signal generator here generating a 60 megahertz signal with a rather snappy 74 picosecond edge on it. Then going through this coplanar waveguide and then measured on channel 1 on our oscilloscope. We then have our probe attached to channel 4.
So here we have the signal generator in yellow. We've zoomed in on the 71 picosecond rise time edge at 500 picoseconds per division on the scope. And before I attach the probe, I'm going to save this as a reference so we can see how the signal generator is loaded by the probe when I attach it, which I'm going to do now. So here we have our three traces. We have the original unloaded signal generator trace in orange, the loaded signal generator trace in yellow with the probe attached, and the probe response is in green. So first of all, let's look at how the signal generator is loaded. We can see that there's a very small change in peaking there, and we can also see that the rise time of the signal generator has increased from 71 picoseconds to 74 picoseconds, around a 3 picosecond increase. So really, this signal is barely being touched by the addition of this probe, a very subtle set of changes there. Now, looking at the probe response, its rise time is around 110 picoseconds, which is the fastest it's ever going to be given its bandwidth. And in this context, we're not really expecting an accurate representation of the source because the rise time of the source is too fast for the probe, which will lead to distortion. And also the measurement point of the scope and the probe are separated by around 1 meter of coax. So first of all, we have our 9-volt battery box, the probe itself. This guy has a SMA connection, but BNC is available as well. We measure three things on every probe: the bandwidth and the frequency response. We measure the tip capacitance, and finally we measure the return loss with a 50 ohm transmission line with the probe attached. And you get one of these with every probe. Then we have some copper tape. This can be useful for improving grounding. Then we have our box of tips. Starting off with our resistive signal pin. This connects in the signal socket. Then we have our angled ground socket. And into the angled ground socket you would place a sprung ground pin. Now this is sprung so that if you are probing a circuit, you don't have to get the angle of the probe exactly right. You've got a bit of wiggle room there with that spring. And then the angled nature of that ground socket means that you can actually access ground connections that are varying distance from your actual measurement points there. We then have some spares and some solderable tips there as well. This stand is weighted. We have a fairly large hunk of steel in there to keep it weighed down, and we also have rubberized feet to stop it sliding around. And we have these exchangeable clips that slide into the stand as such, and that just clips just below the coax connection here on the probe. And that will give you a nice, firm, stable platform for the probe.
For our next setup, we have two active probes measuring a USB 2 high-speed signal. USB 2 high-speed is a differential signal the probes measuring the two sides of one differential pair, the positive swing and the negative swing. So here's the packet from a USB 2 signal. We have some synchronization bits at the start and then a payload towards the end. So let us zoom in on, first of all, the synchronization bits. So again, we have the two signals inverted one from another, and then I have here a signals of the subtraction of the both, which of course improves signal quality. So yes, this is a 240 megahertz repeating signal, and the rise time is around 500 picoseconds. So again, comfortably within the bandwidth of this probe. We can then zoom out and have a little look at the data payload, because when we look over here, we can turn on persistence and create another eye diagram. And there we have our very nice eye diagram, our two differential signals, the subtraction, and of course very easily achieved just with a few seconds of setup to attach both probes with two stands and a very nice non-intrusive measurement of our signal. I hope you liked the demonstrations, and of course see you next time.